This question is from GATE 2022, Mechanical Engineering paper set 2, question number 53. A shaft AC rotating at a constant speed carries a thin pulley of radius r equal to 0.4 meter at the end C, which drives a belt. A motor is coupled at the end A of the shaft such that it applies a torque mz about the shaft axis without causing any bending moment. The shaft is mounted on narrow frictionless bearings at A and B, where AB is equal to BC is equal to L is equal to 0.5 meter. The taut and slack side tensions of the belt are T1 equal to 300 Newton and T2 equal to 100 Newton respectively. The allowable shear stress for the shaft material is 80 megapascal. The self-weights of the pulley and the shaft are negligible. Use the value of pi available in the on-screen virtual calculator. Neglecting shock and fatigue loading and assuming maximum shear stress theory, the minimum required shaft diameter is dash millimeter. Let's find this out. Now, as per the maximum shear stress theory, we have the maximum shear stress in a member that is subjected to both bending and torsion is given by 16 pi d cube under root of bending moment square plus torque square. Now in this case we have this torque is nothing but mz, T is mz, which we need to indirectly find out using these tension in the belt drive. So this will be equal to the difference of tension here, net tension on the pulley, which can be calculated as tension on the taut side minus tension on the slack side, T1 minus T2, into the radius of the pulley. This is nothing but mz. So this will be equal to T1 is given to be 300, T2 is given to be 100 into R is given to be 0.4 meter. So we'll get mz as 200 into 0.4, which is 80 Newton meter. Unit that we get directly is Newton meter because force is in Newton and radius is in meter. Now next thing we need to find out M, bending moment on the shaft. T we have already found out, and we need D. By maximum shear stress theory, we should know that this maximum shear stress should be less than the shear strength given, tau S. So tau S is given to be 80 megapascal. So we can use the limiting condition taking this as equal, which will give us the bare minimum radius required in order to satisfy this condition. Maximum shear stress in the shaft should be less than or equal to the shear strength of the material of the shaft. So let's find out M now. Second thing, for bending moment M, we'll construct a free body diagram of the shaft. Let this be the shaft. This is point A, point B, and this is the pulley at point C. So at the pulley we see two tension values, T1 and T2. Here we do not take the net tension, but we take addition of the two because both forces are acting downwards. So we need to take both of them together. This force will be resisted by the supports. So at the roller supports we will have the reaction values. Let this reaction be RB, this be RA. Now this system has to be in equilibrium. So using the equilibrium equation, summation of moment about point A equal to 0. We will have RB into L. This will create an anticlockwise moment. We have taken anticlockwise positive minus T1 plus T2 into 2L. So this is creating a clockwise moment and therefore we have taken it negative. This will be equal to 0. So substituting these values, we'll have the value of RB. Let's rearrange and find RB. RB will be equal to T1 plus T2 into 2 because dividing L throughout we'll get 2 here. This will be equal to T1 is 300, T2 is 100. So we have T1 plus T2 as 400 into 2. RB is 800 Newton. Now we can find RA from here. RA will be equal to T1 plus T2 minus RB. 400 minus 800. This gives us minus 400 Newton. So negative sign means that the sign that we have assumed for RA is wrong. Actually RA is in downward direction. So we can mark this like this. Now we need to find out the bending moment on the shaft, and that to the maximum value of it, because we always design for the maximum values of moments, loads and torque. So let's do that. Maximum bending moment here will be acting at the center because we can see that this is a symmetric structure. We have 400 Newton downward on left side, 400 Newton downward on right side. And at the center we have a 800 Newton load. So definitely we know that this is a symmetric structure owing to the symmetric loading and symmetric geometry. So bending moment will be simply 400 Newton into this distance L, which will occur at the center. Therefore, M will be equal to 400 into L. The value is given to us as 0.5 meter. So we substitute it here, 400 into 0.5, which is 200 Newton meter. Here also we get the unit as Newton meter. So let's write the first equation that we have written. So as mentioned, according to the shear stress theory, the maximum shear stress in the shaft AC should be less than or equal to the given shear strength value for the material. So we can use the limiting condition, which is tau max is equal to tau s, to solve the question, that is to find out the value of T. Therefore, we can write down, according to shear stress theory, tau max is given as 16 by pi d cube under root of bending moment square plus torque square, as we have written earlier. So substituting the values, we have 200 square plus 80 square. We have substituted the values in Newton meter itself. So we'll get the value of D in meter later, which we can convert it into millimeters. So this should be equal to 80 Newton per millimeter square. So this Newton per millimeter square has to be converted to Newton per meter square. So we convert it by multiplying it to 10 to the power 6, because we divide it with 10 to the power minus 3 square. So when we take that in the numerator, it becomes 10 to the power 6. Now rearranging this will give us the value of d cube. D cube will be equal to 16 under root 200 square plus 80 square by pi divided by 80 into 10 to the power 6. This gives us the value of d cube as 1.37 into 10 to the power minus 5, and taking the cube root on both sides will give us value of d as 0.02393 meter. We need to multiply this with 1000 to convert this to millimeters, will give us 23.93 millimeters. Let's go back and fill in this answer. So the minimum required shaft diameter is 23.93 millimeter. To learn more about shaft couplings, you can refer to the NPTEL video, lecture 20, Shaft Couplings 1. It is from the course Design of Machine Elements. The course is taught by Professor G. Chakravarti. He is from Department of Mechanical Engineering of IIT Kharagpur. I hope this solution helps you clear your doubt. Thank you.